has your microphone.
He still has the microphone.
Yeah.
Can I ask you to remove your name tag?
Thank you.
All right. Next talk is going to be by Yossi Azar, load balancing with duration predictions.
Okay, thank you for coming. Thank you for inviting me to the workshop. This is joint work with Niv Buchbinder and my master student Tomer Epstein. And I'm going to talk about load balancing. So this is where the parallelism is kicking in. I mean, there's no other parallelism except of load balancing between machines. Let me start with the offline problem, and then I'll continue with the problem that I'm looking at. So we have m parallel machines. We have n jobs. And we need to assign the jobs to the machine, like obvious. But the machines are unrelated, which means that each job on each machine has a different load. One machine is good in memory, one is in CPU, one is in bandwidth, and so forth. So this is the unrelated machines. There is a special case, interesting special case, which is called the restricted assignment, which means that the Pij is either infinity or let's say 1 instead of Pj even. Interesting case, it's 1. That some machines can process the job and some cannot. And then, okay, let me give you an example. So we have 3 machines. This is the first job. So the load on this machine is 2, on this machine is 1, and this machine is 3. So this is an example. Okay, and now we want to define the load on machine. If the load is defined in the obvious way, just the sum of the loads of the machines, of the jobs assigned to a machine. This is like the straightforward definition of load. By the way, if you have questions, just interrupt me at any time during the talk. And the natural goal is just to minimize the bottleneck, which is just minimizing the maximum load on any machine. Because typically, like the loaded machine are slow in that sense. Okay, this is mathematically just the minimum, the maximum over all the loads over all the machines. Okay, so here's an example. Here are 3 machines, 3 jobs. So let's say the first one is here, the second one is here, and the third one is here. Again, this is a vector. This is a single job. And this is just the load on each machine. And so the load is 3. And alternatively, if we will put it like that, then the load will be 4, which is a little bit worse. And of course, like in this case, the optimal solution is actually to do it in this way, and then the cost is 1. Okay, so I hope that the problem is clear and obvious. Okay, and now, okay, it's a well-known problem starting from Lenstra, Schmois, and Tardosh. And they show the problem is NP-complete, and there is a nice two approximation to the problem in the offline case. Okay, so now instead of the offline problem, I'm talking about the online one. So what does it mean, an online problem? That instead of in the offline problem, all the jobs are given in advance. Here, the jobs are arriving one by one, and we need to assign it to a machine immediately without waiting for the next one. So this is jobs arrive one by one and should be assigned irrevocably to machines. So here is an example, the same as before. We have the first job. Again, it's a vector. It's the load on each separate machine. We decide to put it on machine 1. Now we get another one. We decide to put it on machine 2. And the third one, we decide to put again on machine 1. The cost is 3. OK, so what are the natural algorithms for the online problem? Greedy algorithms, typically, seems like very natural, assigned to the machine with the minimum load. With the minimum load. Alternatively, you can assign it, another greedy algorithm is to assign it to a machine for which the machine is most efficient, which means that Pij for this job is minimum. This is another greedy algorithm. And a third one is assign the job to the machine that after the assignment, it will be minimum. So these are all three variants of three different greedy algorithms. Unfortunately, all of them are omega of m competitive. So I don't have here a definition of competitive ratio, but the ones which are not from the theory. Competitive ratio is the same as approximation ratio, which means that an algorithm is called C competitive if the cost for any possible input is at most C times the cost of opt. So that means that this algorithm, each of these greedy algorithms can be as bad as M compared to the optimal solution. And typically in competitive analysis, we prefer to get a constant if possible, but logarithmic results, which is and M is exponentially worse than logarithmic results. So all these algorithms are bad, but fortunately for this problem, there exists a log M competitive algorithm. I'm not going to describe it now. I'm going to defer for the description for the algorithm for later, and I'll explain later why. Okay? So this is the online related machines. Now, instead of looking on what's called the incremental problem, which jobs only arrive, now we want to look at the fully dynamic case. The jobs all arrive and depart as well. So I call it temporary jobs. They arrive and later depart. So jobs may depart over time. It arrives at time tj, it departs after a dj unit of times. And again, the load is not, we're not looking at only the final load, we have to look at the load at any point of time, because it's not necessarily, the maximum load doesn't necessarily happen at the end. It might happen in between, because it's a dynamic version. So the goal function, is instead of only maximum over machines, it's also over time, because it's a dynamic version of the problem. Yes?
Assuming that the load is corresponding to the runtime?
Okay, excellent question. I was now supposed to say it. There is no relation between load and time. So it's two separate x's in the following sense. You might have large job with short time, large job with long time, short job with small job, with short time and small job with long time. The duration is for how much you need a service, and the load is how extensive is the service at any point of time. So it's completely two separate x's, no relation between them.
You looked at the correlated version of the problem?
No, typically, yeah. Mm-hmm. Yeah. It's because in many, in previous literature, it's typically assuming that these are two separate x's, not correlated. Yeah. Mm-hmm. So the load does not correspond to a time. I'll give you an immediate example. Here's an example. Here I have three machines. This is the timeline. At time one, I get a job. Again, this is a single job. It's a vector over the machines. And it has a duration too. So I put it on, let's say, on the first machine. The cost is 1. Now time advances. At time 1, I get another job. Now it has a longer period. The window is between 1 and 5. And I put it on the second machine. And now the cost is 2. Now I advance. And now the first job already disappeared because it ended. And I advance. I get another job. It has a single duration of a unit. I put it here. Then I advance, then it disappears, and so forth. And this one disappears. So it's a dynamic version, arriving and departure of jobs. Yes? That's the next slide. So that's exactly what we are discussing. Excellent. Yeah. Clavariant versus non-clavariant. So the question, upon arrival of a job, do I know what the duration, or I don't know what's the duration? Okay, that's the definition of clavariant versus non-clavariant. Clavariant means that you know the duration upon arrival, and non-clavariant, it means only when it's leaving, you know that was the duration. And please note that the load is known, because when a job arrives, you have to know how much it's going, what would be effect if you put it on any machine. So the load is known, but the duration is unknown, possibly unknown. So here are the previous results. Okay, so for the clavariant case, we can get a logarithmic bound. So previously, for the permanent version, we had log m. Here we have log m plus log d. D is defined to be the ratio between the maximum duration to the minimum duration. So this is what's the variance in the duration. So it's also getting you in the log. However, the non-covariant one has a lower bound. This is exact bound, and has a lower bound of omega of m, or upper bound of omega of m. So it's exponential gap between knowing the duration and not knowing the duration. Sorry, this is the upper bound. This is the lower bound. The lower bound here is, it's not exactly d. It's square root of d, where the low bound here is omega of m. By the way, for restricted assignment, the m is replaced by square root of m, but still there is, in both versions, there is exponential gap between knowing the duration and not knowing the duration. Yes?
Is the duration always an integer?
It doesn't matter, but I need the minimum duration. So the d is the ratio between the largest to the minimum, smallest, but it doesn't need to be. There is no issue of integer integrality here. It can be arbitrary numbers. Yes?
Is the lower bound against an adaptive adversary or an oblivious adversary?
No. The lower bound is against optimum.
No, this is lower bound on the competitive ratio, right?
Yeah. So it's the online algorithm compared to the optimum offline algorithm. What do you mean, adaptive or not? I mean,
I think the related thing is it randomized?
Oh, deterministic or randomized.
Yeah.
Sorry.
Yeah.
All lower bounds are also for randomized algorithms.
Lower bound, okay.
Yeah. I got confused. Yeah. You're right. I mean, it's the lower bounds are all the upper bounds are deterministic, all the lower bounds are randomized. Okay. Yeah. Okay. So there is a huge gap between. I mean, you want to use the covariant one, but sometimes you don't know the duration. So in many cases, you have only estimation. You know the duration, but only approximately. So you have estimation. So you have estimation of d tilde instead of dj, so each job. And so let's say that the real size, this is the estimation. The job could be either shorter or longer. And of course, estimation can be produced by machine learning or other analysis of the system. So now, I mean, we want to get an algorithm that uses this estimation. Of course, the quality of the solution would depend on the quality of the estimation. Yeah, and I want to know what's the dependence of the performance versus the quality of the estimation. So now I want to how to measure the accuracy of the estimation. So of course, some of the jobs could be underestimated and some of the jobs could be overestimated. And the mu1 is the underestimation ratio, which means by how much the estimation is lower from the real time, from the actual time, and the overestimation is exactly the opposite. And I look at the worst stretch over overestimation and underestimation, and my error is going to be just the product of the two. Okay, so this is by how far is my estimation from reality. This is the definition of my error measure. And again, so note that these are the results for covariant and non-covariant. And now, when I want to add the estimation, I want to see what would happen to this result. So which algorithm should I use? Let's say that my estimations are correct up to a factor of 2. I might not know it, but let's say that they're correct up to a factor of 2. So one possibility is to say, okay, since I don't know the duration exactly, let me use the non-covariant algorithm. But then I get square root of m performance, which is pretty bad. Interestingly, what we prove that if we use the exact estimation, then you lose quadratically. Instead of having a performance which is log m plus log d, you get log m times log d. But our main result will be the following. Actually, surprisingly, by not using the estimation correctly, you can return to have log m plus log d. You improve quadratically. It's a bit surprising. It means that even if you don't know the processing time exactly, but up to a factor of 2, you still get the same competitive ratio as if you would know the exact duration. So you don't need to know the exact duration. Although, the difference, if there is a ratio of 2 in the estimation, the value of the solution can be different. Although the value of the solution is different, the competitive ratio remains the same. It's a bit tricky. You have to think about it a little bit. Now, so this was for an error of 2 for arbitrary mu. The competitive ratio will be here. You must lose linearly in mu. That's obvious. But the assumption is mu is typically small. Yes?
Question. You took the product of U1 and mu1 and
Yeah.
mu2. Why does that make sense?
Okay, it has its advantage and disadvantage. Let's say that all the estimations are, okay, one thing you can think of one-side error. One-side error, the other one is 1. Yeah, so then you should pay, you say why the product is not the maximum. This is your question, or?
Yeah. Why didn't you take the maximum mu1 and mu2?
The product sometimes is better than the maximum. It looks counterintuitive. Let's say that all the estimations are between 10 times to 20 times the real duration. So the product actually would be 2 and not 10 or 20, because one of them could be less than 1 even. I agree. The difference between the maximum and the product is at most quadratic in the maximum.
Right.
So if you want to look at the maximum, it will be mu squared instead of mu. But sometimes it's better. It's a bit tricky, yeah. But yeah, that's it. Okay. And a lower bound, by the way, okay, this was a lower bound even if we know the duration exactly. But if we don't know the duration, if we have an error, actually, I mentioned before that you have to lose linearity, which is not necessarily true, because our lower bound is only square root. We don't really know if you really need to lose linearly only square root of few of the error. Okay, so now I haven't yet specified the algorithm. I didn't say anything about the algorithm. So to specify the algorithm, I'm actually planning to talk about a more general problem. It is one of these cases that solving a more general problem is in some sense easier or easily stated. Not necessarily easier, but easily stated. So instead of solving the L infinity norm, I'm going to solve the LP norm. LP norm is just the sum of the P powers of the load. So this is the LP norm. And nicely, to approximate the L infinity norm, you have to use P which is equal log M. M is the number of machines. So up to a constant factor, approximating the maximum load is the same as LP norm for P equal log M. This is called softmax. I think people have used it in a different context. They used it here in the completely different context. But this, again, approximating the maximum norm can be done by LP norm for P equal log M if you have vectors of size M. This is by trivial algebra. It's not something deep. It's a one-line proof. Yeah, this is one-line proof of softmax. So I'm actually trying to minimize the LP norm over time so now the LP norm is of the vector of the loads, not only the maximum machine, but the vector of the loads on the machines. But I'm still looking at the maximum over the time because the problem is dynamic and I'm interested in the worst time in this problem. So what would be our result for LP norm? They're similar. Instead of log M, we have here the norm. The norm would be at most log M. So this is the upper bound. And this is for error 2. This is for arbitrary error. So it's the same as before. And the lower bound is approximately the same. Let me skip it. Again, just replace P by log M. Sorry, you replace log M by P. OK, so now in order for describing the algorithm, I'm going to give some intuition. So what I'm going to do is span the future. I'm looking at each separate machine. This is the current load, but in case no other jobs will arrive, the current load is going to decrease over time. Yeah, this is assuming that I know precisely the duration, because jobs are going to depart. So I'm going to look at this as I'm looking to actually to span all the future and see what's going to happen if no other jobs will arrive. Now, when I get a job, and let's say that the duration is 2, but let's say that it's the real duration, when I put it, I have to put it over two time steps. That will be the new snapshot of the right time, the current time, looking over all the future. So, yeah, if I put it here, that will be the change and so forth. That will be what will be effect on the future if I put the job on its machines separately. Okay, so the algorithm, so this is why I decided to postpone the algorithm to the end, because it looks like an ugly slide, but actually it's very simple. I mean, it looks a complicated formula, but I'll explain what does it mean. Okay, no proofs, yeah, so you can relax. So the idea is as follows. It's a kind of a greedy algorithm on the LP norm with some slightly differences. So what this does mean, this is the current load. I'm planning to put the job on the machine that after I put the jobs and compute the LP norm and sum it over the time between the current time until for the duration of the job, this will be minimized. I'm choosing that machine. There is some difference that I'm not actually using here 1 over p. We use a slightly, from technical reason, we use a different parameter which is required for the proof that I'm not going to explain, but the algorithm is almost greedily on the LP norm, almost. So this is the load if I would put the job on this specific machine. And the competitive ratio is the required one. So now this, if I would know the duration precisely. If I don't know the duration precisely, I just put the estimate. And as I told you before, if I just put the estimate, I'm actually losing quadratically. I'll put here, the load will be only estimate. And I'm actually going to lose quadratic in the competitive ratio. So it's going to be log D times P and not log D plus P. And the trick, which is a bit surprising, is that I have to use the maximum possible duration. Instead of using the actual duration, I'm putting in my equation, choosing the correct parameter. Instead of thinking that the estimate is correct, I'm actually taking into account what will be the longest possible duration. And once I plug it in, I succeed to reduce the competitive ratio quadratically, from quadratic to linear, and get the required result. I know that this slide is a bit far-fetched, but you can look at the paper. So here, again, although the duration, the estimation is 2, since the error will be one direction will be 2, I'm actually pretending that the duration is 4, and just use the algorithm with the known duration. And that's it. That's the whole algorithm, where the algorithm with known duration is almost greedy with the appropriate norm, with with a tiny difference. So this is it. This is everything. And summary. Yes?
Sorry, I might be remembering it correctly. I thought when you had the algorithm or the problem without duration,
Yes.
you said the greedy solution wasn't competitive?
So this is what I explained. If you use the maximum, then it doesn't work. If you replace it with soft maximum, so solving the LP norm is in some sense easier, not easier. The algorithm is easily stated than solving the infinity norm, and you approximate the maximum norm by the log m norm. And then it's not precisely greedy, as I mentioned, it's almost greedy with a different exponent. Yeah. Yes. Summary. Yeah, if you don't have other questions. So again, the upper bound remains like, yeah, let's think about mu as a constant, then it's p plus log d, which is exactly as if, I mean, you compare yourself, I mean, you don't know the duration, the optimum knows the duration, and still you achieve the same result as if you would have known the duration. So you don't really need to know the duration precisely. You need to know it only approximately. And the lower bound is, again, it's not exact, but it has all the correct terms, but not at the right combination. Yeah, that's always the problem. Not the right combination, but it has the all correct terms. Open questions, and I'm finishing. So first of all, closing the gap between mu and square root of mu. Our upper bound lose mu, the lower bound square root of mu. Yeah, for arbitrary case, a general case, only overestimation, underestimation. And a problem which is unrelated is, again, even without estimation, there is still a quadratic gap between the dependence on the duration. Is it logarithmic or it's square root of log? It's not clear for what's the right dependence? Is it logarithmic or square root of log? And that's it. Yes?
So what's the intuition for why looking at the max possible duration is the right thing to do?
Okay, because the intuition is that error to one direction is more influential than error to the other direction. Like, you want to, like, it's a worst case in the sense that you say, okay, I'm not sure if the duration is small and actually it's longer, the fact that I'm ignoring the effect on the future could be crucial. While if I assume that the job is slightly longer and actually it's slightly shorter, the error is less significant. But the real reason that it came out of the formulas, I didn't put the proofs. When you do the algebra, the formula and the proof, then it just, if you use the maximum instead of the actual estimation, then just everything disappears correctly. Yeah, I didn't put anything about the proof it's quite technical. It's not very complicated, but it's only 2 pages of technical, 2-3 pages of technical things. But yeah, I mean, sometimes it's hard to understand why. I mean, like, it is a bit surprising that one direction, that there is a difference between using the accurate estimation and using the overestimation. I mean, like, to begin with, you thought, it must be the same. There shouldn't be any difference. But somehow, by the formula, this is what happens. I cannot explain it to a deeper level. Yes?
I'm just wondering how robust your algorithm is to the knowledge of the estimates. So what if, for example, you don't get an estimate for every job, or there's a large cost for calling your ML black box to give you the estimate? How does that affect your bounds?
Yeah, I mean, the problem is that if you have a period of time that all the estimates are incorrect, then you can get, since it's a dynamic version, so jobs can arrive and depart, arrive and depart, arrive and depart. So if at a certain time you have incorrect estimation, then at that time, and we're looking at the worst time over the sequence, so you are going to have a big problem at that period of time. So it is.
Missing one of those is the problem.
Yeah, so it is. Yeah, since it's not only incremental, it's also decremental. So you have to be correct at any point of time, which is a bit. So you are sensitive to these errors. Yeah.
Have you talked to the ML community about whether your notion of error is a good one to use?
Yeah. I mean, it is used. It's reasonable. It's a stretch. It's the ratio, because the duration. I mean, there is no. Yeah. I mean, it's the natural.
No, it's fine. I don't know the ML community. I just know there's a lot of different measures for error.
Yeah. Mm-hmm.
Okay.
Yes.
So since your algorithm, as I understand it, uses the maximum, does it change anything if we reformulate the problem as, instead of giving an estimate, I give a guaranteed upper bound?
Okay, excellent question. What I sweep up under the carpet, I don't need to know any of these parameters in advance. I describe it as if I know all the parameters in advance. Actually, I learn is not the correct, learn not in terms of machine learning. Learn instead of in terms of, I see what happens. I evaluate the parameters during the algorithm. I don't need to know anything in advance. I don't need to know the error in advance. The performance depends on the error, but I need to know nothing in advance. Of course, the number of machines and the load, but I don't need to know the error, I don't need to know the duration in advance. I need to know nothing. Yes?
I'll just, slightly separate, I'll just motivate the idea of the predictions, just to say that the paper that's just appeared in ML-SYS, the Systems Conference this summer, with a bunch of people from Google, where we actually look at, in their data center scheduling, taking advantage of predictions on the lifetime. So it's something that they're really doing. There was a paper from people at Microsoft a few years ago about looking at this. Again, it's mostly, there's some theorems, but it's mostly systems work. And then we actually showed that if you can update your predictions as you're running, you can get improved performance. And actually so this Google Cloud systems now actually are using predictions on the durations of jobs in their scheduling algorithms. So it's not this objective. I'll say, it's not this exact objective, but
Yes.
But the idea, just to motivate, and actually, and to sell this, the next workshop we have, the first talk, will be by one of the co-authors of that paper, and he'll be talking about that and other things. So this is, it's real that there are, using predictions in scheduling in real systems.
Oh, okay, great. We are not updating the prediction over time.
Right.
I mean, we assume that that's it. But yeah, maybe you can get advantage of updating the prediction. Yeah.
Any other? We're all motivated now, but we're done, so, okay. All right.
Okay. Thank you.
Pick up again at 2:00.